Veronica.
Sharing. Yes, thanks to all the chairs and speakers so far. So it's my pleasure to introduce the third speakers for today from Northeastern University, Malih Alikhani and Resmi. Malih is an assistant professor and also member of the Northeastern Ethics Institute, focusing on designing inclusive and equitable language technologies with an emphasis on biases and machine learning for critical applications like education, health, and social justice. And Resmi is a researcher, a postdoctoral researcher at the Institute of Experiential AI, working on projects involving fairness, privacy, and robust evaluation, also for high stakes AI applications, and focusing on social benefits, including fairness, explainability, and utility. Yeah, you have the floor. Thank you very much.
Let me share my screen.
Yeah, works.
Oh, well, thank you so much, everyone, for having us. We're very excited to be here. The talk is gonna start with sort of a little bit of overview of what might cause different biases and what might sort of influence from a societal perspective the deployment of fair or biased medical systems that are trained and developed with AI. And then I'm going to pass the mic to Reshmi, who's going to tell you all about a recent project about the bias in multimodal medical data that is used for decision making. And the context of our talk, of course, we're both working in the US, is about the events and the regulations and the data sets that are available in the US. So um, AI is revolutionizing many sectors, and this is sort of past certain point of where we're thinking about AI creating certain vaccines or contributing to drug discovery. AI is helping with rehabilitation of patients, especially multimodal AI in terms of the hardware tools that are designed, but also the software, whether it comes to speech impairment or different sort of other rehabilitation and disability. There is now different influence of AI in parts of Africa and US on food production and the quality of food and agriculture, and so on. And so it is sort of really hard when we talk about AI in medicine or AI in health to distinguish between food and discovery and what actually happens at a doctor's office, whether it's interaction with AI or diagnosis. Next slide, please. And so, Brian Christian, I'm going to lean into this very interesting metaphor that Brian Christian in his recent book called Alignment uses, that there are several things that can go wrong when we look into AI systems and deployment of them. And and he looks at this sort of from two different broad categories and perspective. One is hard alignment, when we actually want to make decisions and think about, okay, so this is the AI systems with certain limitations, with certain capabilities. How do we make sure how sort of what's the right way to deploy it for treatment recommendation, for drug discovery, or for medical diagnosis? And then there is another part where he calls soft alignment, and soft alignment problems are issues where we look into inside a probabilistic model and we see different biases, different alignments within the representations of our transformers and language models. So there's sort of large set of values as a society that we're working with, and we want to encode them into these AI systems. And then there is another part that is sort of not so much what we want, right? It's sort of learned in the representations, and they can cause all kinds of issues when it comes to deployment of AI systems for any applications, really. Here are just a handful of titles from New York Times and famous newspapers that are talking about biases and issues in AI. Next slide, please. So this is one example, again, that has received a lot of attention in the tools that are actually deployed, that are used for healthcare in the US. And this is the observation is that AI algorithms may increase healthcare inaccurate decision making in healthcare for darker skin tones. One example of that is sort of the reaction of these oxygen level measurements tools when it comes to that are sort of attached to fingers of patients for Black patients, particularly in the US. There are several other cases where we see sort of different cancer diagnosis or other algorithms that have been biased, and some of these have been deployed. And so I want to leave with this question in the introduction that there is we may never be able to completely remove the bias, right? And so part of that would be when and how we think about deploying it. And that is also part of the sort of the ecosystem of debiasing, because not all of it is correcting the probabilistic representation, but ways we think about deploying these systems. Next slide. And so I want to say sort of one similar example was that has been happening with AI, where AI has been used sort of the biased facial recognition systems resulted in arresting wrong people, wrong targets, wrong people. A very sort of recent example in the US that made news was this the arrest of a pregnant woman in Chicago, and it was wrong. And so this example I'm particularly picking because it's one of those that after several instances, now, because we know we can't fix the models, policy is going in to correct for these. So for example, how can we bring in human in the loop? How can we make sure there are several tests or multiple systems working against each other before we actually take action and recommend that? Next slide, please. And part of that issue in the US at least is whether it's limitations for debiasing for deployment of models, especially when it comes to medical data, is that we want to keep this data safe in our country under the same protocols. Like we don't want to send medical data that might be attached to certain identities to different countries for it to be restored. And that requires data centers, the development of data centers where we train models and where we save data. And these data centers have been cited as a root cause of an expected 20% increase in utility prices. So anywhere in the US where you see the increase of the development of data centers, there's been increasement in prices of electricity, of food around it. And so it's changing basically the ecosystem. So on the one hand, we want hospitals to use the state-of-the-art medicine, diagnosis tools, for example. On the other hand, they are influencing the health, right, or food access, or electricity access, or welfare of certain communities, different side of the US. Next slide, please. So I think I'll pass on this one. I explained it. Okay. So how can we create more people-centered future when we think about AI and medicine? It is a topic, and I want to sort of draw attention before we dive into a case study that is purely machine learning. I wanted to tell you about what other things we can do and how they might influence the deployment of different multimodal AI systems in medicine. Next slide, please. So one of them is this very recent legislation in healthcare that we have in the US Congress now, introduced by Senator Baker from California, that aims to regulate decision-making process in healthcare. Now, one of the steps that they're taking here is, we need to make sure at several stages that the systems that are deployed are fair, or at least the people, nurses and doctors who are working with those systems are aware of the details that they're working with. And what they're recommending is that it shouldn't be up to necessarily the person who's in charge of purchasing these softwares in a hospital, but there has to be a standard national regulations, institutions such as NIST or different institutions that go and evaluate those systems and really put together explainable guidelines so nurses and doctors know what numbers mean, what they are looking at. Next slide, please. And I think if we can go past the legislations for data center, one more. Next slide. There is this sort of broader framework that we also have here that was presented that was introduced in the Congress by Senator Markey from Massachusetts, our state, was called AI Civil Rights Acts. And the AI Civil Rights Acts really sort of approach this problem from multiple perspectives. It comes to the point where when patients are getting results of recommendations by AI, or if doctors are using it, it has to be transparent to patients. Patients should know what systems have been involved, how their data has been used in training. And the systems need to be evaluated, as is stated in this bill, by a third party. So if Google is developing a product for health, it shouldn't be Google only who is testing it. It should be other institutions who are looking into it. And so it's not passed yet. We'll see. But the bill suggests very interesting approaches when it comes to deployment of these systems. Next slide. Now I'm gonna pass the mic to Resmi, who's gonna tell us about multimodal patient data and what goes into sort of what I call the soft alignment of how can we align representations, probabilistic representations better with our goals and values and serve patients better.
Thank you, Malih. Let me share my screen first. Okay. Is it visible now?
Yes, looks good.
Sure. Okay. So Malih sets a groundwork for me to build on top of it, what she already said. So how we can eliminate the fairness challenges when we learn with multimodal data. So this Mimic 4 dataset has been already introduced by the previous speaker, where we have like data collected from 2011 to 2019. So we have like patient-centric records, like clinical notes and hospital demographic and lab test details, and also ICU details like observations and medications, and electrocardiogram data, emergency department details, and chest X-ray. So this Mimic 4 is a combination of around 40,000 patient data, which is used for public, like in the research community, for analyzing the AI models built on top of the healthcare data. So in our study, we'll be using Mimic 4 and another version of Mimic 4, which is called Mimic I, which is a kind of small scale data set. So which includes the Mimic CXR, that is the chest X-ray images, and then the radiologist eye tracking and like the eye gaze and reflex details. So it is kind of how the radiologist annotate through the chest X-ray and then go for a decision on based on all the patient details plus the chest X-ray. So this will be the patient directory. So we will have the data from Mimic 4 plus the reflex and eye gaze data from the radiologist. So these are the two data sets that we are going to use in our study. So all the results are based on these two data sets. Okay, so one problem that we always face when we do have a multimodal data source is how we can integrate data from multiple sources. So there will be 4 to 5 multimodal sources, heterogeneous sources, and integrating these data to a common source is always directly proportional to its performance at the end in the decision making. So there is one gold standard way of learning or integrating data or the knowledge from multimodal sources, like having separate encoders for each of the input. For example, if you have text, then we have a text-specific encoder, and if you have image, then we have an image-specific encoder. And then we fuse these encoding. It can be like a vectorized representation of the modality, and then we do classification on top of it. So this is one of the golden way of approaching or integrating data from multimodal sources. So one problem with this kind of integration when we have multimodal data is that we are not integrating data to a unified feature space, because we are like relying on different modalities or encoders on top of like modality specific encoders, and then we are fusing it. There is no way of interpreting what integrated data that we have obtained from multimodal sources, and there is no unified feature space aligned in this other than fusion techniques there, where they learn the cross model features and things like that. So we found this is actually directly correlated with the performance, because the way we integrate data is actually have a great importance in the performance of the multimodal model. So we came up with a new strategy where we learn representations from all the multimodal sources in the form of text. So for example, we have tables, notes, events, lab, and X-rays. So for example, in the case of tables, what we have is like we like mask, and then a part of the codes or disease we mask, and then we ask the model to generate the textual representation of the corresponding table. And for example, if we have notes, then we do pre-processing, since it is already in the text. So we do pre-processing, and then the textual representations are learned. And for example, if we have events or labs, and then we do repetition filter, like there will be so many repetitive events, and then we do an outlier detection on the lab, and then corresponding textual representations have been learned in this space. And for the X-rays, which is the specialty of mimic eye dataset, where we have images and the corresponding radiologist eye gaze data. So first we identify the regions of interest of this image, and then we train a binary image classifier in order to detect some abnormalities, if there is any abnormalities present in this image, and then we rely on GPT-2 medium large language model for converting that descriptions to textual form. So we have now a unified textual representation over here, which is very interpretable, because if we have any doubts in learning the representation space, we can actually come back here in textual representation and the corresponding multimodal patient records, and just have a correlation analysis between these two. And then another advantage is like Mimic is one of the small scale data set around 15,000 patient data. So we can leverage the use of pre-trained domain specific language models. For example, we have MedBird, Clinical Bird, and Bioclinical Bird, which have been trained on like numerous data like Mimic 4 and different versions of Mimic 4 and other healthcare data sets. So one advantage of using this textual representation is that we can actually leverage this like MedBird and Clinical Bird or domain specific healthcare language models on top of this for getting the exact knowledge from the textual representations or the patient data. And then we embed using this one of the MedBird, Clinical Bird, or Bioclinical Bird, and then we can actually do embedding and prediction on top of the data or top of the integration or the representation that we have learned. So this is one way. So we found that like using this learning representation in the form of unified textual data, which is actually overperforming having separate encoders or domain-specific encoders for each of the modalities that we have. So this is one contribution that we made in the proposed work. Okay, so now we can talk about, so we have the embedding and presentation over here. So we have a classifier which can actually classify what downstream task that we are opting for that. So which is ED disposition task. So which is a binary classification problem aimed at predicting post-visit outcome, because where it is 1 indicate hospital admission and 0 signifies discharge to home. So for this particular case, we also look at individual modalities or individual sensitive features as well as intersectional sensitive features, because because the patient identities or any people's identities shaped by more than one sensitive attribute, as the previous speaker has pointed out. Like we can have like a white female with social education or middle-aged white female. So the identities are shaped by multiple sensitive factors. So in this case, we have individual groups as well as intersectional groups. So we draw the fairness metrics, that is a commonly used fairness metrics in healthcare, like demographic parity, which accounts for the positive prediction in a model's outcome, and the difference in true true positive rate between the sensitive groups or subgroups that we employ here. And then there is another one called worst case parity, which is really good for like the intersectional fairness, because when we have more than one subgroups, so we have to have a measure to decrease the gap between the majority and the minority group. So the worst case parity is just like a min-max ratio. That means if you have a DP measure or a TPR measure, you just take the min of like the minimum value of DP across the group divided by the maximum value of the group, subgroup. So when you reduce those performance, you will automatically attain fairness at the end. So sorry for my bad voice quality, so I'm a bit under the weather. So here in this case, we have the base classifier, which is the classifier from the previous figure. Like this is a classifier. And then we have observed that when we analyze bias of fairness in terms of through the single dimension, for example, white, black, otherization, that is the ethnicity group, or so the DP measure is actually, it's not biased, right? So it's 0.91, which is pretty good fair. So that means we follow 80% rule based on the Equal Employment Opportunity Commission in US. So whatever, which is around a 0.8 and above, it is fair. So in this case, and when we look at the gender subgroup, it is also fair. But when we look at the intersectional group forming between ethnicity and gender, you can observe the WP is very low, that is 0.9212, 0.9712, 0.667, which is unfair. So that means which this experiment or this like brings light how we analyze, how we can obscure inequalities when it comes to intersectional fairness. And also it is also a case for the TPR. So the TPR for the individual group is already biased, but it is actually getting worse than when we come to the intersectional group, right? So this is the experiments that we conducted on the ED disposition task on the mimicry data set, and we found that when we analyze single dimension, maybe the bias is not that evident, but when we go to more intersectional fairness, then the biases are there, and it is more likely to have minority groups in the intersectional subgroup domain. So this is one example. So now we have like the biases we have evaluated, and we have quantified the biases. And next is how we can how we can do bias mitigation when we do with multimodality and to improve the intersectional fairness. So this is a very common notion that we have single attribute based mitigation, for example, pre-processing, in-processing, and post-processing. So when it comes to multimodal data, like pre-processing not really an option, because when we have like individual data sources, and if you do like bias mitigation based only on the uni-model features, when we combine or integrate modalities into a single unified feature space, or some other kind of like fusion, late fusion, or whatever techniques that way, there will be cross-model disparities. So that is one challenge that we are not seeing much work when we use pre-processing for multimodal data. And when it comes to in-processing, already our multimodal model is very big, so we have so many processing inside it. So when we add a fairness penalty to it, it is actually suboptimal. So we have seen papers like in-processing is not a good choice for learning with the multimodal data, because it takes so long to achieve the optimal decision-making process, and also it can affect the overall optimization procedure. And another flexible way of using or mitigating biases post-processing, where we can actually customize the decision boundary for the fairness measure that we want. So this is some of the existing single attribute, single modality based bias mitigation. But we want to explore one a basic notion in the AI literature, which is called ensemble. So there is one recent paper from Cohere AI that they mention that fairness naturally emerges from homogeneous ensemble. The word homogeneous ensemble means we use the same training set, same architecture and same design choices. And then then we actually do ensemble. For example, we have the same classifiers, like maybe 5 or 6 classifiers embedded into one ensemble, and then we use that for prediction. And they prove that this fairness naturally comes from the homogeneous ensemble. And that kind of the problem with so the mentioned they conduct experiment on the DNN, which is called the deep neural networks on image data. So we wanted to really check whether like something is really naturally emerges from our technique. So we want to make sure that that is very generalizable. So we want to adopt their homogeneous ensemble and try if it is satisfies the intersectional fairness when learning with multimodal data. So one limitation for their approach is that is single attribute. They only consider attribute like the sensitive attribute in single dimension, and they conduct the experiments on image modality. So and also this batch order data augmentation. So these are the amount of, stochasticity that we can control inside an ensemble. That means even though we have the training set architecture and the design choices the same, but we can have some kind of stochasticity by just changing the batch order or just having the data augmentation. So we rely on the batch order bit because it has shown greater performance in terms of they prove that the batch order is the greatest among all the homogeneous ensemble that they have tried. So the next is kind of a case study how we can adapt homogeneous ensemble to our approach. So what we have done is we created like 4 to 5 classifiers, and then but the different batch order, and then we evaluated the performance initially with 5 models in an ensemble. So we have seen that in this figure, so the blue the blue shades or the blue lines indicate the base classifier without the ensemble, and the red is the ensemble classifier, that is the homogeneous ensemble classifier. So we can see that in most of the cases, there is not much performance difference between the base performance as well as fairness difference between the base classifier as well as the homogeneous ensemble classifier. So in this case, 0.921, which is for the ethnicity group, and actually when we do the homogeneous ensemble, we got only 0.86, which is actually below the 0.921, right? So there is not much improvement in fairness as they have claimed. And also this is same for the gender group and also the intersectional group. And when it comes to TPR value, this is for the DP values, and the box over here is the WP values for each of the group. And then for the TPR values also, we have seen a little bit performance increment when it comes to individual groups. For example, in this case, in the ethnicity, so like the base classifier is 0.655 and the homogeneous ensemble is 0.728. And then it comes to the gender one, the base classifier got WP of 0.911 and the homogeneous ensemble got as 0.933. But when it comes to intersectional group, it actually decrements the performance of the base classifier. So what we have seen is this homogeneous ensemble is effective when we have a data set with like fewer number of features, and when we focus on like fairness in a single dimension. For example, in the case of gender or ethnicity, but not the combination. So this is the problem with this is like the main reason for this not we have not seen any performance incrementals like the low stochasticity and randomness, because the batch ordering or the data augmentation is not giving much stochasticity between the models, and then we are not observing any performance or fairness increment in this particular homogeneous ensembling when we deal with multimodal data. So we have seen this. So then we came up with and also we have experimented with if there is any change when we increment the number of models in an ensemble, and we have tried from 1 to 15, but we haven't seen any direct correlation between model size and fairness. That means there is not much stochasticity present in homogeneous ensemble, and we cannot generalize the notion that homogeneous ensemble always increment the performance of minority group or fairness of the minority group. So having said this, we came up with another idea, which is called heterogeneous ensembling with a subgroup focus, because our focus is on main focus is on intersectional intersectional fairness, because every patient have intersectional qualities of attributes. So we also use for the heterogeneous ensembling, what we wanted to inject additional stochasticity into the ensembling process. So for that, with a focus on subgroup specific, we divide the entire data based on the intersections. For example, if we have like gender a white female, we have created a data set spread for white female, and then same way, whatever groups that we have created different data set splits for the subgroups that is present in the data set. But one could argue that it is very as the number of data, as the number of like sensitive attribute increases, the degree of this number, the degree is also increases, right? Because we have to create specific data set splits for each of the subgroup intersections. One way of dealing with that, we can actually do a clustering on top of it to get similar features, or to group individuals based on their features, and then use that clustering number as this ensemble science in the heterogeneous ensembling technique. So like here in this particular case, each classifier is trained on a distinct data set split, which is in contrast to the homogeneous ensembling, where we have each classifier has the same data, right? So for each of that means the key idea is each classifier should see the data from different subgroup specific data set split, and then they can specialize or learn the subgroup specific characteristics from the data, right? So this can actually use it for more targeted learning when we have multiple subgroups and things like that. So
Sorry to interrupt. I think we
sorry.
need to wrap up in a couple of minutes in the interest of time.
Sure. Okay, so now we perform the same experiment with the homogeneous as well as heterogeneous ensembling, and we have seen that there is a huge performance increment. For example, in the intersectional group, 0.325 to 0.935, and also like 0.582 to 0.724, which is close to the 80% rule. So it shows superior performance across all fairness measures and the two data sets that we have. And the reason for that is, so the first row is homogeneous ensemble, and second one is the heterogeneous one. So in the heterogeneous ensemble, we haven't seen any leveling down effect. That means for the privileged and unprivileged group, which is like the unprivileged is like the red, and the green. So those performances actually improving. This is the ensemble fairness improvement percentage, and they have the highest disagreement rate between the models, and there is a direct correlation between average disagreement rate and ensemble fairness improvement rate. So this is the idea that we put like our condition, like our proposed method is working under this condition, where the subgroup specific disagreement rate should be directly correlated with the ensemble fairness improvement rate, with a higher correlation of 0.90. So the key takeaway is heterogeneous bagging is fair competent. So for individual as well as intersectional minority populations, where homogeneous bagging may be useful for single attribute and data set with fewer features. And this is one of the challenges that we encountered, which is not addressing in this particular proposed work, where when we have like when we train a model, we have different modalities, but maybe that can be missing in the real world instance. So in that case, the fairness fluctuates or the bias fluctuates. So how can we tackle? So with this, we believe it's a future work in this study. So these are the contacts. If we are open to collaboration, so if you're interested in any of our work or want to know more about that and seeking collaboration opportunities, please reach out to us. And these are the student collaborators that we have from, they are the master students under Malih. So that's it. Thank you.
Thank you both very much for your presentations. So we already have a question in the chat from Alice. Thank you for the interesting talk. Going back to the fusion model, I'm assuming there were also radiology reports associated to the X-rays. If so, how did these compare to the reports generated from the image binary classifier? And did you perform ablation studies on these in particular?
Yes. So we have the in the data set, in the Mimicry data set, we have the corresponding chest X-ray and the corresponding report. So we have actually we have trained a binary classifier to find the abnormalities and do a GPT-2 large language model based report generation, and we just cross-check how the performance varies when there is any in the test. So and we have obtained around 98 accuracy in that. And there are actually models for doing the ablation study, and we have done that, and we got around 99 to 98% performance improvement in that. So due to the time limitation, I didn't include that particular result in this study, in this presentation.
Yeah, so maybe I wanted to ask something related to that, so I'll just jump in. So why would it not make sense to first transfer everything to tabular instead of text? Because it seems to me that the LLM adds like kind of unnecessary information, like the patient has received, but then further down in the training, like those words would not be informative probably. So the words would be selected, which would be already in the table that you start with. So it kind of adds extra processing, but maybe ending up in the same information.
One problem with converting everything to tabular data is like then we have to have specific models for getting information or integrating information from all the tabular data, because the problem with small scale data is, especially in terms of mimicry, we can leverage the use of large language models, then transfer the knowledge from the big data to small data. But I think when we convert everything to a tabular domain, I don't see any domain specific models for converting the tabular data to something else. And also there is a problem with interpretability, because when we learn everything in tabular, then we have to convert that to vectorized or fusion. Then we don't have any, like usable information that we can interpret and that can be transparent also. So I think this is one way of doing it. Maybe there are many ways of doing that, but still, this we found is more interpretable, and it is also enabling like, learning with the small scale data. This is what important, because Mimicry is very small data. So when we perform only on the performance was highly dropping. So this is the way we found to better handle those kind of situations.
Thanks. And there's also a question from Alice Jin. Do you think that the fairness gained by heterogeneous ensembling will transfer to external datasets, especially when there's a shift in demographic attributes?
We haven't performed any out of generalization test in this case. So that could be our extending the future work. For example, like when we have the out of distribution data, how these models perform, what's the robustness in that case? I think that we leave it for a future study, not in this particular proposed paper.
Okay, thank you very much. So maybe in the interest of time, we will now move to the discussion. So thanks a lot again for your talk. And I guess now in the discussion, Amelia, do I need to hand over to you or?
I don't know. I don't have anything specific prepared. We don't have a slide for it, so.
Okay. Yeah, so I mean, we're not a large group, so I think everybody is welcome to participate, or you can also write in the chat. But I guess we wanted to try to talk about, with all of the speakers and participants, about multimodal data sets in general. So maybe one thing that kind of occurred to me while I was listening to all the talks is that I think more recently multimodal is like used in the context of the data really comes in a very different format, so images or text or some kind of structured tables. But I also remember from maybe 10 years ago there was a big rise in multimodal classifier for XYZ. And with that, especially like in the field we're working in, it meant, for example, different types of images, but from different modalities like CT and MR. And I was just wondering for all of your opinions, like, do we need a different terminology for it somehow, so that we distinguish those levels of multimodality, or does it always make sense from the context, or? So any thoughts on this from anyone?
I can start if you want, because
Yeah.
we've had that experience in that we work in this multimodal data set that we presented, but we're also working with multimodal in the old-fashioned way, let's call it. And so far, I think like the context defines it pretty much. And by context, I refer to the venue that we target. So all this old-fashioned multimodal has been within the medical imaging community, and no one has complained, and they understand very well what we meant. I don't know if I do the same for a more machine learning oriented conference, if we would be hardly criticized for using the same term. So my take would be, if you are going to a more computer vision